So what is Thevenin's theorem? Thevenin's theorem is in a linear electrical network containing resistor sources as seen from the two terminals can be replaced by an equivalent circuit consisting of a single voltage source. So we have a single voltage source here from A to B, and this is the open circuit voltage at the terminals. The single series resistors here, this is the equivalent resistance seen from the terminals with all independent voltage shorted and current sources open. So we have to short the source voltage here, this one. So we have the Thevenin equivalent circuit here. So we have the Thevenin voltage. We have the Thevenin resistance here, resistor, and we have the terminals here. We have the uh, load resistor here, and at the end we have the terminals. So why it's useful? Thevenin theorem simplifies any complicated network into a very simple one voltage, one resistor model. So this makes it easy to compute load current, analyze how a circuit behaves when load changes, solve power transfer and maximum power problems, reduce large circuit for small signal modeling. Steps to apply Thevenin's theorem. Remove the load resistor here. So we have the load resistor. Analyze how a circuit behaves when a load changes. So solve power transfer and maximum power problems. Then reduce large circuits for small signal modeling. Steps to apply Thevenin's theorem. Remove the load resistor. Identify the two terminals where the load connects. Right. Then find the open circuit voltage. So we have the VTH here. This is the voltage across the open load terminals. Find the Thevenin resistance RTH. Turn off all the independent sources. So voltage sources replaced with short circuits, and current sources are replaced with the open circuits. Then compute the equivalent resistance as seen from the terminals. So reattach the load. Now the entire network is represented by VTH in series with RTH. So we have example here. If the VTH is equal to 12 volts and RTH equal to 4 ohms, and you attach a load RL, so the load current now is 12 over 4 plus RL. Okay, problem number one, compute the Thevenin resistance and voltage. Draw the Thevenin circuit here. So solution, Thevenin resistance calculations. To find the Thevenin resistance at terminals E and B, we must remove the load resistor RL. Replace the independent voltage source port 8 with the short circuit wire. Calculate the total equivalent resistance between the terminals C and B. Okay, so we have the circuit simplification with the 48 volts source shorted. The resistor R1, 8 kilo ohms, is placed in parallel with R2 here. So R1 and R2 are parallel. This parallel combination is then in series with R3. So it is in series with R3 as viewed from the terminals A and B. So calculations, so R12 is R1 is parallel to R2. So R1 is 8, R2 is 4. So they are parallel. So this is equal to 32 over 12. Calculate the final Thevenin resistance. So RTH is equal to R12. So this is in series with R3. So 8 over 3 plus 2. So the answer is 4.67 kilo ohms. Okay, for the Thevenin voltage calculation, the Thevenin voltage is the open circuit voltage across terminals A and B. when the load resistor is removed. So we have the uh, Thevenin voltage here between A and B when the RL here is removed. Okay, remove the RL. When RL is removed, there is no longer a closed path for current to flow through resistor R3. Voltage at node A, since the current through R3 is zero, the voltage drop across R3 is zero. So VR3 is equal to zero here. This means that the voltage at terminal A is the same as the voltage at the open at the node between R1 and R2 and R3. So we have the node here between R1 and R3, and the node here, this is the node between R1 and R2. So this one I refer to. So voltage divider, the voltage at this node is determined by the voltage divider formed by the R1 and R2 in series across the 48 volts. So applying the voltage divider to find the voltage across R2, which is VTH. So this is source voltage, and we have R2 over R1 plus R2. So we substitute here. The VTH here is equal to 16 volts. So this is our Thevenin circuit now, 4.67, and we have the Thevenin voltage equal to 16 volts. The Thevenin resistance is 4.67 kilo kilo ohm. So solution by Mathematica here. So we have RTH 14 over 3, RL equal to 10. So we have here from the computations. We have also IL here. This is the Thevenin current. So the Thevenin current is 12 over 11. So by using this formula, VTH over RTH plus RL, we have also the IL in the approximate value is 1.09091. Then the voltage here is the Thevenin voltage is 10.9091.